Okay, so today's lecture is a long one, but we are going to make a long story short because it's about elements from group 4A and 5A. We will focus on properties and compounds of carbon first, then we will continue with silicon, and then we will jump to the group 5A, to the most important compounds of nitrogen and phosphorus. As you can see in this table, elements from group 4A and 5A are colored in different way. I mean that there are both green ones, that means that they are non-metals. Blue ones, it means that some of them are metals like lead or bismuth and even tin. While in the middle we got orange cells. It means that they are semi-metals or metalloids. They have some properties of non-metals and some properties of metals as well. About carbon, can you see these stones? So one of them is diamond, another one is graphite. So which one is diamond? What do you think?
I believe maybe the second one.
The second one is gray, more gray at least, yes? So actually the first one is a natural diamond. Oh. And as you can understand, diamond and graphite are allotropic modifications of carbon. They are different. In what? In the crystal structure. Yes? Of course, because diamond is the hardest one, while graphite is a soft material.
In the previous section you mentioned how soon after the diamond
is big N. Okay. How about other resources of carbon? What is CO2?
Dioxide carbon.
Yes, indeed.
The carbon dioxide.
Okay. And the main source of carbon is nothing but those living organisms. Yes? As you remember, oil, gas and coal came from what? From the remains of ancient living organisms. However, there are even some modern archaea species who produce CH4. They are called methanoproducents. And CH4 is a methane.
Yes, methane.
Yeah, so this is one more source of methane. And if we talk about minerals, then calcium carbonate has a lot of polymorphic modifications, and one of them is called limestone. And carbonate of both calcium and magnesium is known as dolomite. So carbon is there in the biogenic material and in non-biogenic one. However, even if we talk about limestone, they say that the most part of calcium carbonate has an organic origin. I mean, from mollusks who lived in a very, very ancient state of the development of the earth. Coming back to crystal lattices. So, there is a crystal lattice of diamond with sp3 hybridization, graphite with layers, and inside each layer we got what? Hexagons. 6 carbon atom rings connected together in layers, yes? Lonsdale light is a diamond with changed crystal structure. They say this is the diamond from meteorites, from the space. And letters D, E, and F show different fullerenes. Fullerenes, they were produced artificially, and they are nothing but just like spheres, yes?
The elements.
And for these spheres, there are a lot of interesting ways to use them in medicine. So,
Yes.
like transporters, they can be conjugated with some kind of ligands to enter specific cells and so on. And by the way, those fullerenes themselves can also have some biological effects. And if you notice, there are 6 carbon rings and 5 carbon rings in those fullerenes. That's why they are not planar, but make a structure that reminds us what? A ball, a football ball.
Yes.
Yes. Also, there are nanotubes.
Tubes.
A tube, yes, a whole one.
Ah.
Nanotube. They also try to use it somehow in medicine, in diagnostics. And if we write some reactions with carbon, most often we mean amorphous carbon. The amorphous one has no definite or ordered crystal structure. How can we call it? A soot, a coal, a burnt wood? Yes? And these are those reactions featuring carbon as an amorphous element. With hydrogen it can form a lot of compounds, as you know, yes? With silicon it forms silicium
Silicium
carbon or silicium carbide.
Boron carbide.
Yes, or boron carbide, and they have what? Atomic crystal structures. In the right side of the slide, this is SiC structure. Again, something like diamond, but it's not diamond.
All of reaction is bond, yes?
They form bonds. Carbon with calcium gives us calcium carbide, CaC2, while the formula of aluminum carbide is Al4C3. There are different types of carbides like this. Yes, carbon monoxide, carbon dioxide, CS2, as you may notice, this is a linear molecule, as well as dicyan and CCN. It's also a linear molecule. Carbon can react with compounds as well, and it acts in many reactions as a reducer, like there. The way to reduce copper from its oxide, as you remember, is to perform its reaction with the coal. There will be CO, CO2, and pure copper. The same story is about iron oxide, but if you try oxides of more reactive metals like calcium, then there will be not just a metal, but mostly carbide. Yes? So carbides are formed with more active metals. Check these reactions like C plus H2SO4 concentrated. So if you put a piece of carbon into the concentrated H2SO4, there will be a mixture of gases CO2, SO2 and H2O. And if you put carbon into concentrated nitric acid, instead of SO2, of course there will be NO2. So, again, as a reducer, it can react with those acids. And not just an acid, but even with a nitrate, KNO3. And there will be N2 as one of the products. An interesting reaction between C and sodium carbonate will give us sodium and CO, and carbon can reduce even sulfur from barium sulfate, and there will be sulfide, yeah, and CO. So this is the answer to some of the chains of chemical reactions about how to make sulfide of barium from sulfate. Only in this way, not in the ion exchange reaction, but in the redox reaction.
So the rate reduces, yes?
Yes. About carbides, as I said, there are different types of carbides, but they differentiate usually ionic or salt-like carbides and metal-like carbides, as well as covalent. If it's ionic one, it means that carbon is in the negative oxidation state and it's in combination with the negative metal. And even this group can be subdivided into different classes, including methanides and acetylides. So methanides in the reaction with water release mostly methane, while acetylides in the same reaction release mostly H2C2, that is acetylene. They have different crystal structures and even oxidation states of carbon atoms. When they are metal-like, it's more like an alloy. Yes, when a metal is mixed with carbon, it still has a metallic crystal structure. Yes, but with carbon atoms as well. It changes the properties of that metal, of course. And when you say iron in everyday's life, remember it's not a pure iron, but it has a certain amount of C. It depends on the concrete mark, I'd say, of that steel. Yes.
Okay.
And when they're covalent, then they form atomic crystal structure. For example, carbon can do it with boron or with silicon. Carbon monoxide and carbon dioxide. Please check these differences in the lengths of a bond. So the bond between carbon and oxygen and carbon dioxide has a length of about 116.3 picometers, while the bond in carbon monoxide is shorter, 112.8. So since it is shorter, it means that it's stabilized somehow compared to the bond in CO2. And do you remember the explanation? They say that there is a triple bond between C and O formed by the way of the sharing of unpaired electrons for C and O, and that's how two bonds are formed, or a double bond, I'd say. While the third one is formed by the way of donor-acceptor interaction between a lone pair of electrons of oxygen and an empty orbital of carbon. So this is the hypothesis, and it's approved by what? By the shorter length. That's how they can prove it, that it's stronger. Okay. Remember that CO can be a ligand in complex compounds called carbonyls. Remember that CO cannot form salts, and it is able to participate in redox reactions mostly, again, as a reducer. What's the biological effect of carbon monoxide? It binds hemoglobin stronger than oxygen, and that's how it blocks the transport of oxygen by hemoglobin. So it's dangerous. The next compound is called prussic acid or hydrogen cyanide. Hydrogen cyanide, HCN, yes? Or, as you may notice on this slide, HNC. And that's the trick about this compound. It can exist, and it exists as a set of isomers, HCN and HNC. And only the last one is really toxic, because carbon, when it has a lone pair of electrons and when it is situated at the edge of the molecule, is able to block cytochrome C oxidase. Where? In the mitochondria. And if cytochrome C oxidase is blocked, then the cellular breathing is stopped. Mitochondria cannot produce ATP anymore. Yes? And that's how, and that's why prussic acid is toxic. The toxic effect is associated with this ability to bind cytochrome C oxidase. The acid itself is a weak one. That's why salts of prussic acid are hydrolyzed. And that's why even not prussic acid is so famous as a poison, but KCN, that is potassium cyanide. And in the right side you can see an anion of what? FeCN6 minus. This is an ion of the red blood cell.
With iron.
Yes, with Cn molecules as ligands. Notice that the bond is formed between iron and carbon, not nitrogen. Why? Because carbon has what? A lone pair of electrons. That's why they can make a bond like this. There are not just cyanides, but also thiocyanates with a structure like this, SCN or SCN with another kind of bonding, either two double bonds or one single and a triple bond. And an interesting thing is that
Three bonds.
in both isomers, carbon is situated in the middle. That is why if we convert cyanides into thiocyanates, this is, yeah, they are much less toxic, and this is the way to save a person who has taken cyanides. Yes, and it can be done with the help of thiosulfate. So thiosulfate and Na2S2O3 can change the situation. Yes, as well as you might know, glucose. But it's not so powerful, unlike Na2S2O3 in the way of the treatment, yes, of the intoxication by cyanides.
Sam țepele după pun mă să mai afli și se estrogén va și sulfur.
About carbon dioxide, there is a question that can come into your exam. Is it polar or non-polar as a molecule?
Polar.
Yeah, but it's not,
No.
because it's linear and carbon is in the middle. If it was at the edge, it would be polar. But when it's in the middle, then there is no dipole for this molecule. And so the solubility is low of CO2 in water, and at 25 degrees per Celsius it's just about 0.03 mole per liter. However, that's enough to make distilled water acidic, because when CO2 gets into water it reacts like this, yes?
Really?
Yeah, it forms HCO3 minus and H plus. So that's how the water becomes more acidic when CO2 from the air gets there. Yeah, that's the story about pH in the distilled water. It's about 5.5 or something. About silicon, there are a lot of minerals of silicon, more than 400, and the most stable one is, of course, silicon dioxide, SiO2. And the SiO2 can form different modifications like quartz, yes. The dispersed one is called sand, yeah, and silicon with concretions of iron and manganese oxides. Yes, this is a stone, can be found in Belarus, for example, in many fields.
And the second one you can find where?
Everywhere.
Yeah.
in the Middle East, especially. And there's just sand and an oasis somewhere.
Very bad video. Very
Yeah,
bad.
snow.
No.
Okay, how can we produce silicon? It can be reduced from SiO2 with the help of magnesium, for example, or with the help of carbon. And also, halides of silicon can be used for this purpose in the reaction with hydrogen. But the most pure one is formed because of the decomposition of so-called silanes, compounds of silicon and hydrogen. However, this procedure should be made in the absence of oxygen. Otherwise, there will be SiO2 and not silicon. This is the crystal structure of silicon in its diamond-like modification. There is also graphite-like lattice of silicon, but it's very unstable. Silicon, as well as, for example, diamond, is hard, but not so hard, but fragile. By the way, as well as diamond. And, as you remember, silicon is what? Is a semiconductor.
Semiconductor. Silicon and germanium is the most usable semiconductor
In the
as I
world.
remember, yes.
Yes. And
Semiconductor.
that's how microchips are working
Yes.
everywhere.
Silicon.
They say even sometimes inside some persons. Okay. When silicon reacts with fluorine, there will be SiF4, and this is the reaction that is possible even at normal temperature. At higher temperature, it can react with much more elements and compounds, for example, with oxygen, with carbon, with nitrogen, and even with magnesium. It forms magnesium silicide, where silicon has a negative oxidation state. Silicon also reacts with water just like a metal, producing an oxide, this time a dioxide, and H2. A philosophical slide. It's about the difference between silicon and carbon. The chemistry of these elements is different. But why? They say because the radius of carbon is much smaller. And since it is smaller, carbon is prone to form double and triple bonds or aromatic bonds, yes? Why? Because the distance is not so long between carbons, and perpendicular pi clouds can be overlapped easily. However, for silicon, yes, because of this distance, there is no good overlap. So silicon cannot form a double bond, at least easily. But still, silicon has d orbitals, unlike carbon. And the presence of those empty d orbitals helps silicon to be more reactive. So that's why compounds of silicon are not so stable compared to compounds of carbon. And this is one of the representations of silicon dioxide, where together with sigma bonds between silicon and oxygen, there are also pi bonds between lone pairs of oxygen, lone pairs of electrons, yes, and empty d orbitals of silicon. And this is the explanation of stability of silicon dioxide. And as you can understand, it's hard, yeah, solid, I say, at normal conditions, unlike carbon dioxide. That is a gas, yes. So they say, why? Because the bonds are very strong, since there are also what? Pi bonds with d orbitals of silicon involved in their formation. There is also silicon monoxide, and an interesting acid is H2SiO3. Why this acid is so interesting? Because it's solid. And again, H2SiO3 is just a simplification of a formula. Really, this is a SiO2 times H2O at different proportions. And down there, it's not just a picture.
Yes.
This is the depiction of the structure of what? Of silicates. So silicates are really what? Poly anionic salts. Because the SiO3 to minus, it's not a long anion, but they form what? Esters like this. So there is a line of those anions connected with each other by ester bonds, I mean through oxygen atom. And how about those balls, violet balls? They show potassium cations situated somewhere there, around this polyanion. Silicic acid may be imagined like H4SiO4, but it's not completely true once again, because SiOH4 times does what? Polymerizes. And once it is polymerized, water is released. And that's why we cannot say even concrete formula. We don't know how many water molecules in this moment have been already released. And that's why this acid forms a gel. And this gel is known as silica gel. Silica gel is used widely. In analytic chemistry, for example, you can adsorb something on the silica gel in TLC. That is what? Thin layer chromatography. It's used as well. And how about the usage of silica gel in medicine? Is it? Or absorbance, for example, yes. But okay, we will come back to this. Silans, or compounds made of silicon and hydrogen. Check the formula, it's just like alkan, but a Si is there instead of carbon. SiNH2n plus 2. Yes? But what's the problem about these compounds? They are very unstable. Once SiH4 is formed, as you can see, it will be oxidized by the oxygen in the air, even at normal temperature. And don't forget that they can react with what? With alkali, unlike compounds made of carbon and hydrogen. So they are much more reactive in this way.
Because the D.
Yeah, they have D orbitals already. And that's one more philosophical question. Why carbon? What does it mean? Why carbon is used in organic molecules? Why carbon-based compounds were chosen by the nature to build the molecules of life? And we can say a thing or two about it during this lecture. First of all, the number of valence electrons of carbon is equal to 4. And the number of orbitals on the outer layer is also equal to 4. So, there are no empty orbitals in carbon. And there are no lone pairs of electrons. And of course, there are no even unpaired electrons. And it means that in compounds made of carbon and hydrogen and maybe some other elements, carbon is very stable. It would not react with a lot of substances, yes? And stability should be one of the main factors that can somehow promote the development of bigger molecules, more complicated molecules, and finally life, yes? And when life appears, when those molecules are starting to reproduce themselves. Yeah? But unstable guys, they cannot do it well, at least, yes? The second reason is that carbon can form single, double, triple and aromatic bonds. Unlike other elements, or the most of them, yes? But carbon does it easily, and again, those compounds are stable, especially aromatic, yes? The third point is that there is partially negative charge on the carbon atom and not on the hydrogen. Unlike in case of silicon or boron, where silicon has a partially positive charge, while hydrogens are partially negative. But once again, those charges are not so high for hydrogens connected to carbon. If there were more positive, they would form what? Hydrogen bonds, for example. But if it's just a compound made of carbon and hydrogen, hydrogens connected to carbon, they are not normally able to form any hydrogen bond. Again, this is what? One of the factors of their stability. And electrons in them are shielded by what? By protons of hydrogen atoms. And coming closer and closer to the inorganic chemistry, hydrocarbons have no acidic or basic properties. So once again, they are very stable. That's why the nature once has chosen them, and not silicon. Cool fact is that fullerenes are compounds that were first synthesized by human, or by mankind, if you like, or womankind. Yeah, by a kind woman, yeah. But later they've discovered them in the outer space. So really they are stable, and according to the spectral data, when they, watch the sky, the stars, some space around stars where the planet must exist, they analyzed spectra, and they found that there are spectra that are similar to fullerenes. That's why they say that they do exist somewhere in the outer space. So maybe not just fullerenes, but maybe some other carbon-based life forms are there, not because of the science fiction, but because compounds of carbon are stable. Why not? There is a chance to develop, yes? Okay, the usage of compounds of elements from 4A group. What is activated coal? A tablet that is black, that can be used during the poisoning to absorb all of the bad things, yes, from the stomach and from the intestines. Na2CO3, calcium carbonate, and AHCO3, they are used as antacids. They react with HCl in the stomach and neutralize it for a while. But carbon dioxide will be released, yes? Fullerenes, as I said, are good things to develop some new approaches to treat, for example, cancer, maybe other diseases, as transporters and as specific binders of some receptors. Isotopes of carbon are used for the analysis, analysis of metabolism. And what is a silicon implant? Silicon implant, what is this?
For dentistry, yes?
No, not for dentistry, they are soft. In the plastic surgery.
Yes.
So those those implants are based on what? On silica gel. This is a SiO2, yes? And also for the lenses in the eye. Yes, there is a lens and there's a need to replace it sometimes. And again, it must be soft enough, yes? That's why it's made of silica gel. And silica gel is made, is used where? I'd say where? In the building of houses, for example. It's a good material to fix something, like those windows, yes?
Yes,
Uh-huh.
it's like
Yes, yes, because it dries out and forms something hard after that. And PbCH3COO2, this is a lead acetate.
Lead acetate.
Acetate. And the cool thing is that some scientists believe that this is the possible cause of the decline of Roman Empire. Have you recognized this picture, by the way? This is a picture from Futurama.
Ah, yes, that guy, Bender, yes?
Yes, with Bender, but it's not Bender. This is what Robot Gedonist.
Yes, I really like Bender. Most
One of the coolest things.
robot.
And this is the robot who is Gedonic. Yeah? And that's what Roman guys did, and then they died out. Why? The explanation, one of the explanations goes like this, that they enjoyed wine, yes?
Oh, yes.
But that wine was cooked in the kettles made of lead. Yes, and finally this compound was produced, PbCH3CO2, and this compound is very toxic, but it's sweet. That's the thing. So when they boil wine in the kettle made of lead, then finally, yes, this compound was formed. They used to eat it as a candy, yeah? And that's how they become intoxicated with lead. This is one of the reasons, a chemical reason for the decline of Roman Empire. Because of hedonistic behavior. Yeah? Okay. About nitrogen. So, nitrogen is the element that is very, very abundant in our planet. At least the air contains 78% of N2. So mostly there is N2 around us right now, yes? As you can understand, there are a lot of compounds made of nitrogen, and namely in the Earth's crust there are salts like Chile saltpeter, Indian saltpeter, and Norwegian saltpeter. So the word saltpeter is the synonym of the word nitrate. And in Chile, they do what? They sell that mineral, I mean sodium nitrate. While in India, they got much more potassium nitrate. And the Norwegian one,
Calcium.
it's calcium nitrate. What's the cool thing is that I've been asking many times those Indian students about what is
Do they need the food? Sodium nitrate.
No, they don't eat it. This is a fertilizer. And also KNO3 is used to make what? A shot. So I've asked Indian guys about what is Indian saltpeter, but no one answered yet. So for us it's Indian, for them maybe it's Russian, or maybe even Persian, who knows. Okay. On this slide you can see as him about the circulation of nitrogen in the biosphere.
Yes.
As you remember, N2 cannot be fixed by us from the air. But who can do it? Nitrogen fixing bacteria in the roots of some plants or directly in the soil, and they convert it to ammonium. And then ammonium is oxidized into nitrites and to nitrates. And other plants, as well as those with symbionts like nitrogen fixing bacteria, they can take nitrates from the soil. And that's why saltpeters that we've mentioned are used as artificial fertilizers. They can put it in the soil and the plants will grow better after this. Okay? The molecule of nitrogen is very stable because there is a triple bond between those atoms of nitrogen. And at room temperature, nitrogen can react only with lithium. And they will form lithium 3N. Yes, lithium nitride. How can we produce nitrogen in the lab? For example, we can decompose NH4NO2. That is nitrogen, what? Nitrite. The products are N2 and H2O. We can decompose N2O into oxygen and nitrogen, and we can decompose ammonium dichromate into R2O3, water, and N2. Also, in the reaction between magnesium and nitric acid of a certain concentration, we can form magnesium nitrate and N2. However, remember that there will be some subproduct, not just N2. And copper O can react with ammonia, and that's how copper will be reduced. Yes, there will be pure Cu and N2 will be released. What's this molecule? This is ammonia. And there is an sp3 hybridization of nitrogen atom, as you remember, and there is a lone pair of electrons upon nitrogen. Ammonium salts can be decomposed. If it's just ammonium chloride, it will be decomposed into NH3 and HCl. If it's carbonate, then NH3, CO2 and H2O are formed, and phosphates can also be decomposed, including hydrogen phosphates. If you heat ammonium sulfate until the very high temperature, there will be finally NH3, SO2 and N2 will be decomposed like this. Yes, with SO2, N2 and NH3. 3 gases will be formed. And about the decomposition of ammonium nitrate. At low temperature, relatively low, like 260 degrees per Celsius, there will be N2O and H2O. But N2O itself also decomposes and forms N2 and O2. That's the story. Everything depends on what? On the temperature at which this decomposition runs. Ammonia is one of the ligands in complex compounds, so it can form our favorite compound that we produced even twice, I guess. Copper NH3 4 times SO4. Yes? Deep dark blue color.
Carbon tetra ammonium sulfur. Sulfate.
Okay, this is sulfate of what? Tetra kappa. Tetra kappa. Without a catalyst, NH3 burns in oxygen and forms N2 and H2O. When it reacts with chlorine gas, it also forms N2 and HCl. By the way, in the most of the cases when there's no specific catalyst, compounds containing nitrogen would form N2, because N2 is the most stable form of this element. That's why ammonia hydroxide can be oxidized by KMnO4. KMnO4 is a strong oxidizer, as you remember, and there will be MnO2, KOH, and N2 together with H2O. In the same manner, ammonia can be oxidized by bromine. There will be ammonium bromide and N2. And also, ammonium chloride can react with copper oxide. Copper would be reduced, and one of the products would be N2 and HCl as well with water. What's this scheme? It shows general structure of amino acid. So if they ask you what's the function of nitrogen in human body, maybe first of the things that you can tell is that nitrogen is a part of amino acids and so proteins, yes? And amino acid can be imagined as a derivative of NH3, but instead of one of the hydrogens there is something organic, yes?
But R has group aldehyde, yes?
R means a radical.
Radical.
It can be different. For 20 proteinogenic amino acids, R is different. Yes?
Yes.
That's the trick. What's this molecule? This is hydrazine N2H4. It's colorless, volatile liquid. And sometimes it's used to speed up an engine in a car. Yes? Because it burns readily and forms N2. Once again, once N2 is formed, a huge amount of energy is released. Nitric acid can be reduced by atomic hydrogen into a thing like this. Hydroxylamine. So, looks like the part of NH3 molecule is connected to OH group. And what is this? This is hydrozoic acid, HN3. So N3 with the minus is what? It's an anion. An ion. Almost linear, but not exactly. Check this picture. Not 180 degrees, but 171. And why are we talking about this compound? Because NaN3 is a sodium azide. That's the favorite reactant to kill bacteria in biochemical solutions. So even when I want to keep a buffer, not for a day, but for a month or two, put a small portion of sodium azide in the solution, and that's how all of the bacteria will be killed. Yes, that's how we can keep solution for a while, thanks to this compound. What's the trivial name of nitrogen 1 oxide, N2O? This is a laughing gas. Used for what purpose?
For laughing people.
To make them smile and laugh.
No, God's standard.
Actually, to put into the narcosis, yes, before the surgery.
Yes.
But after first breath, they may start laughing. Yes. Okay, N2O. How can we produce it? Due to the decomposition of ammonium nitrate. Remember that N2O can react with many substances, for example, with copper. And remember that at 700 degrees it will be decomposed itself into elements. So, as you may notice in the top or at the top of the slide, this compound may be called nitrogen 1 oxide. So what is the valence of nitrogen in N2O? What would you say? And what is the valence of nitrogen in N2O?
Valence?
Yeah. Because in the bracket there is number 1. But actually it's not a valence. But you may say it's an oxidation state rather. And how can we call it in English manner or USA manner? This is dinitrogen monoxide. Dinitrogen because there are 2 nitrogen atoms, and monoxide because just one oxygen. So check it. So what is the valence of nitrogen in this compound? Maybe 3,
Maybe 2.
maybe 4. Because again there are 2 isomers, yes? And one of the nitrogen atoms makes a triple bond, another one make either 1 triple and 1 single or 2 double bonds. And one of them in one of the modifications can give double bond. Everything but not one. And is this molecule polar or non-polar?
This is non-polar.
Polar.
Of course it's polar because oxygen is not in the middle. That's why anyway it would be a dipole. Okay.
Biliyorsun oksijen haddi, kuantum haddi şimdi seviyorsun. Biliyor musun?
Nitrogen monoxide, yes, or nitrogen 2 oxide, is a famous compound because this is a secondary messenger or gaseous transmitter. It transfers a signal. It can do what? Activate guanylate cyclase or cyclase in our cells, yes? And this is the signal for the dilatation of vessels, yeah? And why? Because it's very reactive, short-living molecule, and one of the reasons is that it would react with oxygen to form NO2. By the way, this is the structure of NO, and you may notice that it's nothing but a free radical because there is a single unpaired electron at the atom of nitrogen. That's why it's so reactive. Nitrogen 3 oxide or dinitrogen trioxide is an oxide that exists only at low temperatures as a liquid. In the gaseous phase, it does a decomposition. It would be decomposed into NO and NO2. There is an acid that corresponds to this oxide, that is HNO2. How can we produce it? We can take an O, NO2 and water.
Just one question. For an oxidation, number oxidation 3, yes? What will happen for N2O? This is reaction
Plus, for N2 it's +1,
+1.
but here it's +3. Oxidation state is good. I mean, easy to understand. Unlike valence for those compounds. And remember that HNO2 disproportionates because the oxidation state of +3 is not so stable.
Yes.
It would turn either to +5 and to plus 2, and then continue its chemical reactions. This is HNO2, called nitrose acid, nitrose, yes, with the salts called nitrites. Nitrites can be oxidizers or reducers. So with a strong reducer, they will play a role of an oxidizer. With a strong oxidizer, they will play a role of a reducer. Well, Eksan mentioned some redox reactions, so there are 3 samples of redox reactions that you should know how to complete and how to balance them with the help of the method called what? Electron-ionic redox reactions balancing. This is nitrogen 4 oxide or nitrogen dioxide. How about this molecule? Is it polar or non-polar?
Is it no?
It would be non-polar if it were linear, but it's angular. Since it is angular, this is polar molecule. And this molecule can form a dimer. When 2 molecules of NO2 combine with each other, they form N2O4. And this is one of the very few one-step chemical reactions. The color of NO2 is orange. The color of N2O4 is rather yellow. And that's how we can even try to measure the temperature. If we got a bottle of this substance, when it turns to yellow, then it means that the temperature is lower. When it turns to orange, then it's higher, because delta H of the dimerization is 58 kilojoules per mole with a negative sign. So it's exothermal process. How can we produce NO2 in the classic reaction between copper and concentrated HNO3 when it's concentrated? NO2 has no corresponding acid with the same oxidation state of nitrogen. But anyway, we say that this is an acidic oxide because it can react with water and produce acid or acids. In the absence of oxygen, NO2 will give us a mixture of nitrose acid and nitric acid. So this is a disproportioning reaction. N from the oxidation state of +4 turns to +3 and +5. The same story is with the solution of an alkali. There will be nitrate and nitrite formed in the solution, and instead of NO2 at lower temperature they can write N2O4 with the same set of products. NO2 can be produced in the reaction between nitrite and acid. Why? Because HNO2 is non-stable and will turn into NO, NO2 and H2O. Also, NO2 can react with SO2, and this is the way to produce SO3. At high temperature, however, NO2 would decompose into NO and O2. And finally, the last oxide of nitrogen, that is nitrogen 5 oxide, N2O5. Or as they say, dinitrogen pentoxide. The cool thing about this substance is that at solid state and even in the liquid state, this is an ionic compound. Ionic. Why? Because there is a cation of NO2 with the plus and the 9 of NO3 with the minus. And we can call it nitronium nitrate. while at a higher temperature, as it turns into the gas, it becomes a molecular compound with the formula, structural one, that can be seen on this slide. How can we produce N2O5 in the reaction between HNO3 and P2O5? We can also oxidize N2O3 by ozone, and there will be O2 and N2O5 in a solid state. And N2O5 is the oxide that corresponds directly to the nitric acid, because N2O5 plus H2O will give us HNO3. And here comes the structure of HNO3. We know one thing, that there are 3 oxygen atoms that are all connected to the same nitrogen. However, we should say that nitrogen cannot have a valence of 5, and the maximal valence of nitrogen is 4. That's why we can say that nitric acid exists as a set of isomers that you can see, yes? And actually the bond between nitrogen and 2 lone oxygen atoms is like not single, not double, but 1.5 order bond. Can you see this bottle? This is nitric acid.
Ah,
Why it has such color? Because of the decomposition. It decomposes and produces NO2, while NO2 has an orange color, the color of the tail of the fox. Yes? How can we produce HNO3? First, they run the reaction between nitrogen and hydrogen and produce ammonia, A. Then ammonia is oxidized in the presence of a catalyst to produce an O, and O is oxidized further to produce NO2, and then NO2 plus O2 plus H2O give us HNO3. And another way to produce it is to take a saltpeter, like sodium nitrate, and run the reaction with the concentrated sulfuric acid. There will be NaHSO4 or Na2SO4, and HNO3 will be released as a gaseous substance because it's more volatile than H2SO4. Concentrated HNO3 is a strong oxidizer, but still there are some metals that are resistant to HNO3, like gold, platinum, and some others. Metals like aluminum, chromium, iron, nickel, and cobalt are passivated at low temperature by the concentrated nitric acid, but at the higher temperature they will react anyway. And there are a lot of possible products of reduction of nitrogen. Here you can see a table that shows how the mass percentage of HNO3 and the nature of the metal determine the main product of nitrogen reduction. In general, when HNO3 is very concentrated, there will be what? NO2 everywhere. When it's very dilute and the metal is active, there will be NH4NO3. In other combinations, there may be N2, N2O, and O. But actually, as you may notice at the bottom of this slide, there are usually many products of nitrogen reduction released in the same reaction with the same metal. In the reaction with iron, for example, there is N2, N2O, NO, ammonia, yes, everything. And even NO2, depending on the mass percentage. the ratio between these products will be changed. While if you notice what's happening with magnesium and HNO3, there will be even H2. But the fate of H2 is to react with other products of the same process. So H2 would react with NO or N2O and produce N2. That's why if they ask you, can hydrogen be produced in the reaction between a metal and HNO3, you say yes. But if they ask you, can we collect that hydrogen, that is, you say no, because anyway it will react with something else that is also produced in the same process. The rule about the decomposition of nitrates. If a metal is situated before magnesium in the electrochemical series of metals, its nitrate during the decomposition will turn into nitrite, nitrate into nitrite, and oxygen will be released. If a metal is situated between magnesium and copper, including magnesium and copper, then the nitrate will be decomposed into metal oxide, oxygen, and nitrogen dioxide. And if the metal is very, very noble, I mean it's situated after copper, like silver, then the nitrate decomposition will give us a pure metal, oxygen and NO2. This is a question for many, many tests, many chains of chemical reactions, and even for problems. But remember that nitrites of active metals like NaNO2 at higher temperature would also be decomposed. For example, into Na2O, NO, and NO2. And finally, we should say a couple of words about phosphorus. Here comes the formula of hydroxyapatite. Can you check it? Calcium 5, PO4 3, and either F or Cl or OH. So it would be fluoro, chloro, or hydroxyapatite. Why are we talking about them? Because they all form our bones and teeth. Yes? A thermodynamical table can explain why there are a lot of compounds made of phosphorus and oxygen that are stable, while compounds made of nitrogen and oxygen with the bond between N and O are not so stable. Can you check the energy of those bonds? The bond between P and O is very strong, while the bond between N and O is not so strong. So nitrogen prefers to make bonds to hydrogen or carbon, while phosphorus enjoys oxygen. At the bottom of this slide there is an ancient way to produce phosphorus. They take phosphorite, means calcium phosphate, some coal and some silicon dioxide. Everything from today's lecture, by the way. When they heat it together, they form calcium silicate, actually a glass, yes, and CO, that's carbon monoxide, so it was dangerous for them to do it, and phosphorus, that's the way to produce phosphorus. Phosphorus was one of the two ancient non-metals. I mean non-metals known in the pure state for ancient people. One of them is phosphorus, another one is sulfur. There are allotropic modifications of phosphorus. It can be white, and when it's white it's molecular, toxic, volatile, and white phosphorus can do what? It can show us a beautiful luminescence. When it's burning, it burns with the light. And that's why alchemists enjoyed phosphorus, because it can give some light. When it's red, it's amorphous, and when it's black, it's atomic. So red and black phosphorus is not so dangerous because they are not volatile. Not volatile, that's why that's okay. How about this one? This is yellow phosphorus. It means that white phosphorus in the air is oxidized partially, and also it changes its crystal structure from molecular one into the amorphous one. So it's actually a mixture of what? White and red. Together it's yellow. The molecule of white phosphorus has this strange shape, yes, with 4 atoms connected together, with the angles that are strange, 60 degrees, while it should have been 109 or at least 90 degrees. So this structure explains why they are not stable, those molecules, and why white phosphorus is so reactive. While black phosphorus forms something like graphite, yes? And the red one is amorphous. They've tried to show that there is no order in the connection manner of these atoms. So phosphorus can react with oxygen to produce an oxide like P2O5, and one of the ways to produce orthophosphoric acid is to run the reaction between phosphorus and HNO3. So from P we'll get directly H3PO4, and NO2 and water will be produced. Phosphorus can exist in the negative oxidation state as well, in salts or compounds called phosphides. And if you put magnesium phosphide in water, there will be PH3. That is called phosphine, a compound that is similar to ammonia. This is the structure, yes? But what's the difference between phosphine and ammonia? The difference is in the angle, yeah? Not 107, but 93.5 degrees. And phosphine is not so basic. However, some salts like phosphonium iodide are known. It doesn't behave like ammonia. At least because it will be reacting with oxygen spontaneously. Once it is formed in the medium that contains oxygen, it will turn into P2 or 5. It's not stable. Halides of phosphorus like PCl3 and PCl5 can react with water, and they will be hydrolyzed into what? Into HCl and the corresponding acid, where phosphorus is in the same oxidation state as it was in the corresponding halide. Some words about numerous acids that can be formed with phosphorus. If it's +1 oxidation state, then the formula is H3PO2. This is called hyperphosphorus acid. Please notice that there are 3 hydrogen atoms, but just 2 of them are connected to phosphorus and 1 of them is connected to oxygen. It means that this one can give just what? Just one type of salts, because the ability to form salts depends on the number of OH groups, yeah? So this one is a monoprotic acid actually, not triprotic one, and pKa is 1.2. It's a weak one, but relatively strong. What's the name of this one? This is hyperphosphorus acid. Hyperphosphorus, the oxidation state is +1 for phosphorus. It can be produced in the reaction between P4 and barium hydroxide, and there will be PH3 and barium what? Hypophosphite. This is the structure of P4O6, a molecule while the simplest formula of this oxide is P2O3. The temperature of melting is just 22.5 degrees per Celsius. The acid that corresponds to P2O3 or P4O6 is called phosphorous acid. The previous one was hypophosphorus. This is just phosphorus. The oxidation state is +3, and as you may notice, there are two OH groups already. So it's a diprotic acid, while one hydrogen atom is still connected to phosphorus directly. An interesting fact is that, again, it can form an isomer, that is POH 3 times, but the equilibrium is shifted towards the existence of a diprotic acid. pKa is 1.3 for the first act of dissociation, and it means that phosphorus acid is weaker than hypophosphorus one. A little bit, but still weaker. And it can form two types of salts, since it was a diprotic one. And this is P4O10. That is the molecule with the simplest formula of P2O5. This is the oxide that corresponds to not phosphorus but phosphoric acids. And one of them is called metaphosphoric acid. That is just HPO3. And also it corresponds to the orthophosphoric acid. What's the difference between meta acids and ortho acids? For ortho acids we got additional water. So if there is additional water, then it's H3PO4. And this molecule is a molecule of a triprotic acid. There are three OH groups, so orthophosphoric acid can form how many types of salts? 3. Phosphate, monohydrogen phosphate, and dihydrogen phosphate. pKa for the first step of dissociation for orthophosphoric acid is 2.148. It means what? It means that orthophosphoric acid is even weaker than phosphorus acid. Strange but true. And how about the ability of those phosphates to polymerize? Of course they can. They can form linear polyphosphates or branched polyphosphates. By the way of what? Formation of esters. They are connected through oxygen. While if they form something cyclic, then it would be metaphosphate. So metaphosphoric acid is nothing but the polyphosphate that is cyclic. That's how a water molecule is lost. Among polyphosphoric acids, we can mention diphosphoric or pyrophosphoric one with a formula of H4P2O7. Pyrophosphates are produced in many biological syntheses. Yes? And what's interesting is that this acid, polyphosphoric, pyrophosphoric acid, is stronger than orthophosphoric one. What is this? Do you know this compound and its properties? So actually it contains 3 phosphates, yes, and they are connected with each other and form a linear polyphosphate. And what do you know about the bonds between them? They are called macroergic. They say that they store a lot of free energy. Once it is broken, a lot of free energy, as they say, is released. Yes, that's the story. So ATP is a molecule that can store the energy, as they explain it. What kind of energy do they mean? They mean the free Gibbs energy. not any other energy, but this one. What is this? So there are phosphodiesteric bonds in DNA and RNA where the same phosphate is connected to what? To two sugars, either deoxyribose or ribose. And as you may notice, RNA is also forming a secondary structure. Also, please keep in your mind that phosphates can be covalently connected to proteins, and this is called phosphorylation. The mechanism from the chemical point of view is again the formation of a ester bond between the remaining part of phosphoric acid and OH group. And there are three amino acids that have OH groups: serine, threonine, and tyrosine. They have OH groups. So covalently proteins can be phosphorylated by what? By serine, threonine, and tyrosine residues. But also phosphates can be bound by different binding sites that contain either positively charged amino acid residues or even negatively charged but able to form hydrogen bonds. So don't you confuse covalent phosphorylation and just the binding of phosphates. It's a different story. And phosphorylation, as you might know, is the way to regulate the activity of an enzyme. Some enzymes are active in the phosphorylated state, others are active in the dephosphorylated state. Well, that's how they regulate. They are regulated. Yeah.
Or you should say force SER. This is
This is one of the amino acids. It's not an element. It's amino acid procedure. And how can we detect phosphates? We can detect them in the reaction like this with ammonium molybdate. The color on the final compound is yellow. This is a test reaction to get caught those phosphates in a solution. The easier one is the second one, where an H3PO4 can be revealed by AgNO3, and there will be Ag3PO4 as the yellow precipitate. Okay, so today we finish, but later we will continue.